Hey everybody, welcome back. This is lesson 5 for our social justice math class. We are going to be looking at data and proportions today, specifically how we collect data. That's going to be one big thing we're going to look at. And then also kind of the problems we run into when we try and collect data and when we try and use that to make inferences. We are going to touch on some sensitive subjects, but they're mostly adjacent to sensitive subjects rather than directly talking about them. So if at any point that becomes an issue, feel free to stop and reach out to me. So let's start with an example. Right? This is a few years old, but when these slides were made, I would say probably 4 or 5 years ago, something around that ballpark. These were the numbers that we were able to find. So there are 350 million guns in the United States at least. And then at that time, the census estimated the current population to be under that at 324.7 million. So there are more guns in the US than people, at least there were at this time. And one of the top reasons people give for owning guns is self-defense. So a study that really tends to highlight this, and one that's referenced quite a bit, is called the CLEC study. You can see it down there at the bottom. Every year, there are 2.5 million instances of defensive gun use in the US, right? So that is a ton of these things, right? If we kind of break that down a bit, then that would be one incident for every 130 people per year, right? So taking our population at Spring Hill College, that would be something to the effect of, 7 or 8 students would experience some sort of defensive use of guns every single year, right? Now, this could be a true thing, right? Even though that feels like a lot. And that's because there are some instances where certain subpopulations have a higher instance of something happening. So an easy example of this is STD rates in college students. I'll let you put 2 and 2 together on that one. But this is something where in the general population, it's much lower, and then college students tend to spike that number. So when you look at an overall average, it looks higher than it is in general. But how would we know whether or not, right, there is a subpopulation that sticks out here? How would we know if the study is trustworthy? So there's 3 kind of questions that come to mind. First off, where did this 2.5 million figure come from, right? That is what they're claiming, right? Is one of the ways they could do this, right, using the government's records to figure out how many uses of guns there were and then how many defensive uses there were, right? And then the main question that we really should be asking ourselves anytime we come across something like this is, should we buy their conclusion? So to answer in reverse order, no, right? Not saying they're wrong necessarily, but taking it at face value is not exactly the smartest thing to do. The second thing, did they just use records? No, right? There's very, very little kept on this unless something is officially in a police report, right? Then there isn't a record of that, and even those can be difficult to get a hold of because you have different levels, right? Whether it happens in a municipal sense or in a state sense or a county sense or anything like that. So even if there are some records, they are very spread out, but they do not encompass, nearly any substantive portion of what we need to look for. And where did they get this 2.5 million figure? Well, the CLEC study surveyed about 5,000 people. So to be clear, when I say they surveyed 5,000 people, what I actually mean is they asked a bunch of people and about 5,000 responded to that. So when they got their answers back, 66 of the 5,000 that replied reported having a defensive use experience with a gun, right? And so if we look at the proportion of respondents that made this claim, we can do 66 over 5,000, right? And when we extrapolate that to the US adult population at the time, right, that gives us the 2.5 million figure that had a defensive use experience. So we already saw some issues there. We'll come back to them. So if you're keeping track in your head, don't forget those, right? But let's take another look at an example and kind of figure out what goes on as well. So we have 7,870 women that were asked about the circumstances surrounding their pregnancies. These were US women, and this was a British Medical Journal study. Now, 45 of these nearly 8,000 women reported at least one virgin pregnancy unrelated to the use of assisted reproductive technology. Right, so if we take a look at this here, right, 45 women out of the 7,870, we can come up with a proportion that reported having some sort of virgin birth experience, right? And if we do that, we put the 45 over the 7,870, right? Do that math out, it gives us about 0.5%. So as a decimal, it would look like 0.0057. As a percentage, we move that over twice, it's 0.57%. So about 0.5%, right? So to be clear here, right, what is happening is these women are asserting that their pregnancy was not the result of any sort of sexual contact, and it was not the result of any sort of assisted reproductive technology, right? So this is something that, right, is quite a bold claim to be made, especially when you consider, right, one of the major religions in the US and across the world has this as kind of a cornerstone of its faith. So if we take that number, that 0.5%, right, that feels small, but there were 3.9 million births in the US in 2013. So if we look at 0.5% of all of those, right, we would do 0.57 times 3.9 million. All of a sudden, that starts to give us a large amount. I think it's just over 200,000 virgin births in the US in 1 year. Right, so let's go to the study and see what they say about this fact, because obviously that's not something that we would take at face value and believe, right? So the study says 45 women reported at least one virgin pregnancy unrelated to the use of assisted reproductive technology. Although it was rare for dates of sexual initiation of pregnancy consistent with virgin pregnancy to be reported, right, it was more common among women who signed chastity pledges or whose parents indicated lower levels of communication with their children about sex and birth control. Right, so now we can start to see the truth peeking out from behind the curtain, right? You have kind of two things going on here, right? Either women who are unfamiliar with how the process works, right? They have not been taught what would cause a pregnancy and what would not, right? They have not been taught about birth control or anything like that, right? And then you have women who have some kind of incentive to not have had any sort of sexual contact with anybody, right? Women who sign chastity pledges, right, maybe feeling pressure from their family, maybe feeling pressure from their community, from their religious body, anything like that, that can cause them to want to not tell the truth in a situation like this. And it's hard to blame them, right, when so much is at stake for them personally, right? So the study came up with this conclusion. They said around 0.5% of the women consistently affirmed their status as virgins and did not use assisted reproductive technology, yet reported virgin births. Even with numerous enhancements and safeguards to optimize reporting accuracy, researchers may still face challenges in the collection and analysis of self-reported data on potentially sensitive topics. Right, okay, so now we see another aspect of something that can go wrong with these studies. So let's go back to the CLEC study. So if you had anything in your brain locked away for that one, time to bring it out now. There's a couple issues with how they approach this. One, their questions were asked in a leading manner, right? So leading manner indicating that they were asking questions in a way that elicited that they wanted a certain answer to happen. The second is that men in general tend to inflate the number of times they use their gun, right? Some men can see it as a masculine thing, or they can see it as part of their identity. And so that is something that they will do sometimes. And then the other thing that happened is just what if their 1.3%, so the percent who had a defensive use experience, was a fluke, right? What if it was closer to 0.7 or zero point 0.3, or what if it was even higher, right? What if it's actually 1.5 or 2%? When we have all these things kind of playing together, that in combination with taking a small study like this, which 5,000 people is fairly small in the grand scheme of all of the adults in the US, right? And we apply that to a very large population, small percentage changes can have very, very big consequences. So 1.3%, right? If we drop that down to 0.3%, that's taking away nearly 3/4 of the defensive use experiences. If we bring it up to 2%, that's almost doubling it, right? So there's a lot going on here with regards to how those small percentages can play a large part when we extrapolate like this, right? So a second study, right, analysis of the National Crime Victimization Survey, which had a sample of 90,000, found that the actual number of defensive uses for guns is around 100,000 per year, not the number that the CLEC study gave us. So it's pretty clear here from these two studies, right, that there are certain biases that pop up when people are investigating things like this, right? And some of those biases may be on purpose, right? There may be some kind of reason, either monetary or influence or power or something like that, that people would want things to pan out a certain way. Sometimes the biases are just an artifact of our evolution, of our upbringing, of the experiences we've had. So the good news is you can at least trust me, hopefully. I try my best, but even I am not free from biases. And so when you have something like this that you're investigating, whether it be gun use, whether it be reproductive technology, or anything of that nature, right? Anything that's important to you, and you come across something that kind of makes you stop for a second and think that that doesn't feel right, that doesn't sound right, or something that surprises, go, wow, I didn't realize it was that much or that little, right? Then you want to take a minute and kind of investigate that, right? Now, doing that is tough. It requires time. It requires a lot of mental energy, right? You can't research everything. You just literally can't, right? So if you hear something that sounds off, right, dive a little deeper. It usually takes a couple minutes, right, of scrolling through the internet, looking for the original article, reading through something. But those couple minutes can pay off in a big way, especially if it's something that's very important to you or has a drastic impact on your life. All right, so let's switch topics here a little bit. Now that we've talked about some of the things that happen with our data collection and our extrapolations, let's see how this stuff is actually used, because realistically, when we are doing these studies, we are trying to come up most of the time with probabilities. So if we go back to our data visualization lesson, right, we pulled this from here. We have female veterans, right, in various stages of their career, right? We have the percent enrolled in college. So our dark purple here is veterans, and our light purple is non-veterans. So if we look at this very first bar over here, we have 33.7% of early career veterans, right, are enrolled in college. So first question is, how would we use this proportion, right, this 33.7%, to estimate a probability, right? So what we want to do here is really just take that 33.7% and kind of reframe it a little bit, right? This is our sample, right, that we've gathered, where we have about a third, right, 33.7% of our female veterans aged 18 to 34 enrolled in college. And so we just want to reframe it in a way that says, if I were to go out and select at random, right, from the entire population of female veterans between 18 and 34 years of age, if I were to randomly select one of them, right, what would the probability they are in college be? Right? And this can give us a good estimate. Now, this is not going to be exact. This is not going to be perfect because, as we saw, extrapolations can sometimes get us in trouble. but they often serve as a good jumping off point to start discussions. So a good estimate may be 33.7%, or we could even generalize it further and say about a third, right? So if I go out and randomly select a female veteran aged 18 to 34, right, the probability that they would be enrolled in college is about one third, right? Or if we want to be specific, 33.7%. Again, that's not the actual probability necessarily, but it is a good guesstimate, right, that we can get from our sample and from our proportions. Right, so using this, we could say, well, Alabama, at the time I came up with this, had 7,694 female veterans aged 18 to 34. How many would we estimate are enrolled in college? We could say, okay, well, this 33.7%, right, gives us a good indicator of the percentage that would be enrolled, right, a proportion or a probability. And so we could say, I would expect about a third of these female veterans to be enrolled in college. So I could take this 7694 number right here, right, and I could divide it by 3, right, because about a third. Or if I wanted to be more specific, I can multiply it times 0.337, right, change this percent to a decimal. So I could do this 7,000 number times 0.337, and that would give me a more exact idea of exactly how many Alabama female veterans aged 18 to 34 are enrolled in college. Right. So when we have these proportions, we've seen the dangers of scaling up, of extrapolating. Scaling down tends to be much more useful. If we know a lot more information about the general population, it's much easier to talk about a subpopulation as opposed to doing it in the reverse. Right. So we have some other numbers here. We have the US population, we have the world population, we have the prison brief estimates for the incarcerated population in the US and the world incarcerated population. And we have some questions here we want to look at. So suppose we select one member of the US population at random. What is the probability they are incarcerated? Right. So, okay, so let's look at our proportion here. Our proportion is going to guide us to the probability. Right. So if I want, right, a member of the US population and I want the probability they are incarcerated, we've done a little bit of this before, but we're going to make a fraction. We're going to put the thing we're interested in on top, or the amount of people or things who have the property we care about. In this case, right, the property that we care about is that they are currently incarcerated. Right. And then on the bottom, we're going to put the total population that we're interested in. So specifically here, it's the US population. It's not the global population. We're only concerned about the US right now. So what we would do is we would say, okay, well, there's 2.145 million people in the US that are incarcerated. And our US population at the time was 326 million. So what I'm going to do is I'm going to take this number, 2.145 million, and put it over 326 million. So this will be the top of my fraction, 2.145. The bottom of my fraction will be 326, right? And that will give us our proportion in, well, the units don't matter at that point. They're both millions, so we're good to go there. So that will give us our proportion straight away, right? Now let's see if we switch things up. What if we randomly select one member of the global population? What is the probability they are incarcerated? Well, we have to switch up our numbers here a bit because our view has changed. We're no longer talking about just the US, we are talking about the world as a whole. So we need to use the world number of incarcerated people, so this 10.578 million, and we need to use our world population here, 7.423 billion. So now our units don't match. This is still going to be the top of our fraction here, this 10.578. Right? And the bottom of our fraction is going to be this billion number here, this 7.423 billion. We just need to make sure the units match up. So there's a couple ways to do this, right? Depending on how you want to do it. You could just get rid of the million and billion and just write it out with all the zeros in all their glorious splendor. So you could do 10, right, comma, 578, comma, 3 zeros, comma, right? I know that it'd take care of it. You just need 3 zeros there. This one's the one that needs the more zeros, right? So 7, comma, 423, comma, 3 zeros, comma, 3 zeros. Right, write it out with all the zeros, let stuff cancel out, and you'll be good to go. The other thing you can do is just change this billion into a million, right? And just move this decimal over 3 places. So 7.423 billion is 7,423 millions. So we can convert one to the other, right? If you're confused on this, I don't blame you at all. It's kind of tough to explain in a video. So feel free to reach out to me. Or if you want, you can use Google or your phone or anything and just say convert 7.423 billion into million, right? And your phone will do it for you. And once you do that a couple times, you'll start to notice the pattern because the pattern doesn't change, right? So you do that a couple times, I think you'll be good to go, right? Now, suppose we randomly select one person from all of the incarcerated people on the planet. What would be the probability they're in the US? So I'm gonna let you pause for a second if you want and try and figure this out on your own. I'll give you a sec. Okay, so here, right, again, we want our top number to be the thing we're interested in, the bottom number to be the total. So our total here is all of the incarcerated people, this 10.578 million, right? All the incarcerated people on the planet. And the probability they're in the US, well, there's this many incarcerated people, right? And then how many of those are in the US? 2.145 million. So this would be the top of our fraction here, this 2.145, and the bottom of our fraction will be 10.578, right? And that would give us our probability there. Okay, so let's talk about proportions a bit, right? We've already discussed a little bit about what happens with them. Right, so let's consider an example where we have a one-question survey, right, that we give out to a subset of the population, and we're going to restrict our potential answers to yes or no. So we're asking one question, and the response we're expecting is either a yes or a no, right? We can create a fraction dividing the number of yeses by the total number of responses, right? Similar to how we did in the previous slide. Right, this would be called a sample proportion for yeses. So this proportion we generally write as P with this little caret figure up top. We'll call it P hat because mathematicians are allowed to have funny names too. Right, so P hat here is just the number of yeses over the total size of our sample, right? And that gives us the proportion of people who answered yes to this. Now, is this the same as the fraction of the entire population that would have answered yes? Probably not, right? When we take a sample, all we can get is some kind of estimate, and that estimate varies based on a lot of factors, how good it is. But again, it points us in the right direction here, right? So we have our actual proportion, right? Whereas if we asked every single person in the population we're studying, we have the number who would say yes over the total size of the population. That's kind of like our end goal. That's what we're trying to estimate here when we take a sample. So we're going to call that P. It doesn't have a hat on, right? It's just P, right? And that is our population proportion for the number of yeses. We usually don't know that. It's usually impossible to find that. So we often used P hat to estimate what P is going to be. We survey some number of people, find out X number of them said yes, and then P hat would be the number that said yes over the total amount of people we asked there. So knowing this information, right, if we know P hat, the proportion of yeses, what is the proportion of non-yeses? It's pretty easy to figure that out. All you have to do is do 1 minus whatever your proportion is, because everybody who didn't say yes said no, because there are only two possible responses, right? So if 3/4 of the people said yes, I do 1 minus 3/4, that would give me 1/4, right? And 1/4 of the people would have said no. Those would be our non-yeses, right? So what we can do here is we can say 1 minus P hat, 1 minus our proportion of yeses, give us our proportion of no's, and this Q hat is going to be our proportion of no's. So P stands for yeses or successes, Q stands for no's or failures here, right? Now, if we have more possible answers to a question, we can always separate it into something and not something, right? If I ask what your favorite color is, there's a lot of different possible answers to that, right? But I could always say, well, let me look at the number of people who said green and the number of people who didn't say green, right? Or I could say, what's the number of people who said yellow or orange? And what's the number of people who didn't say either yellow or orange, right? So here, right, we have Mobilians preferring Carpe Diem to Starbucks in a blind taste test. This is made up. But we can look at the sample proportion of Mobilians that prefer Carpe Diem to Starbucks. Now, obviously, there's other coffee places we could look at, but just looking at these two, right, P hat would be the number who preferred Carpe Diem over the total number we asked. So that would be 320 over 400, right? That would be our proportion. And we could reduce that down. We could turn that into a decimal. All of that is fine. But as long as we have the right number there, the form doesn't matter too much, right? Now, if we want to go the other way, what is the proportion that do not prefer Carpe Diem to Starbucks? Well, if 320 said Carpe Diem, right, and 80 of them didn't say that, then they would have had to have said the other thing, right, which is that they did not prefer Carpe to Starbucks. So it would be 80 over 400, the total we asked, right, and that would give us that number. All right, here's another example. We asked 10 students if they're keeping a cat in their dorm room. 2 of them admitted to keeping a cat. What is our sample proportion of students keeping a cat? Right, well, 2 of them admitted to keeping a cat. 10 of them we asked total, so 2 over 10, that's 1/5, or that's 20%. So our sample proportion is 20%, 0.2, 1/5. Again, the form doesn't matter too much as long as we get the right idea there. Right, so what exactly does that tell us? Well, we could extrapolate that and say 20% of all students are keeping a cat in their dorm. And then we have to ask, do we think this estimate is close to the actual proportion of students that are keeping cats? Right, well, let's break that into a couple other questions. How would we find the actual proportion? Right, well, there's a couple ways, depending on how brute force we want to be about it, right? We could ask all of the students instead of just the 10. But just like we saw earlier, right, there are some issues here where maybe a cat would, or maybe a cat wouldn't admit to wanting to be in a student's dorm. Maybe a student wouldn't want to admit having a cat in their dorm, especially if it's against the rules. So we might get a situation where a lot of people lie here, right? So how can we improve the estimate? Well, find the actual proportions a bit out there, but some things that we could do, right? We could ask more people rather than just asking 10. We could ask 100, right? We could ask 200, right? The more people we ask, generally the better the proportion would be. Maybe if we make it anonymous, right, students would be more likely to report that they have a cat because they wouldn't be worried about getting in trouble if that were against the rules. So those are some things we can do. Now, increasing the sample size, that's called the law of large numbers. The bigger sample we take, the closer to our actual proportion we get, right? So that is always something to keep in mind. If you can take a bigger sample, I definitely would, right? Now, let's suppose we know that about a fourth, so 24.7% of full-time Spring Hill College undergraduate students are first-year, first-time students. So this is their first year in college, and this is their first time in college, right? So they did not attend a community college before this. They did not do any sort of college during high school or anything like that, right? So 24.7%, that would be RP. Let's say, right, we consider our class to be a sample of full-time Spring Hill College students. We could figure out the proportion that were first year full-time. Now, obviously, with an online class, it's a little more difficult to do that, but that's okay. We could still find that proportion if we wanted to, right? We could send out a survey to everybody and ask, right? Or we could try and find that information ourselves. What we're going to find is that if you do that, those proportions are probably not the same, right? And then the big question is, if they're not the same, that's expected, but if they're really far off, then would we maybe think something's wrong with that proportion we're being told, this 24.7, right? So how different would P hat and P have to be for you to think something's going on, that maybe the information we're being provided is not correct, right? So that leads us into our next lesson. I'll let you ponder that for a little bit. Here are some references for the things we talked about in some of the studies we discussed, if you want to look closer at those, right? As always, we have our homework for this week. You have hopefully already gathered your data for last week's worksheet. And then this material will be on test 2. So this actually is correct here, where we want to have this worksheet completed for test 2, and we're going to turn it in at the end of this 3rd week of our summer course, if you're taking the summer course. So thank you all for watching. Thanks for your time, and I'll see you in the next one.